Okay, stats, let's do chapter 9, section 1, estimating a population proportion. Let's first start defining a few terms. A point estimate is the value of a statistic that estimates the value of a parameter. We do this often when we run an experiment and we try to take a mean and we try to say something about a population. We're trying to estimate. But, our estimations may not always be super accurate, but they should be close depending on what our sample size is like. So in July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalties for persons convicted of murder. 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. That's just a fancy way of saying divide how many were in favor by the total number of people. So this p hat is x divided by n, so that's just 1,123 over 1,783. Just the number who said yes, which is approximately 0.629. So that's all they're asking you to do, is to find the decimal representation, divide your fractions. But what we're really going to focus on in this chapter is how to figure out how accurate our estimate is. And that brings up the main theme of chapter 9, which is a confidence interval. Now, a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So in a random sample of registered voters, 53% favor candidate A with a margin of error 3%. What's the confidence interval? Well, if you have your mean and your error, to get the upper end of your confidence interval, you add the error. To get the lower end, you subtract the error. So that would be 0.53 plus 0.03 or 0.53 minus 0.03. Now this can be written just with a plus or minus instead, or you can simply add them and subtract them and put them in what I call interval notation or less than and greater than equal to notation. But we know how to get p hat. The question is, where did this error come from? How are you going to be able to find the error? That's what we need to focus on. We need to focus on how we can find the error using some of our tools. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted 1 minus alpha times 100%. Okay. The most common level of confidences are 99, 98, 95, and 90%. We'll talk more about that. So for 99%, it says alpha is 1, because 1 minus, or 100 minus 1 is 99, etc. For example, a 95 confidence level has alpha 0.05 because it's in decimal form instead of percent form. Means that if 100 different confidence intervals are constructed, each one may be a little different because it's different samples, but 95 of them should have the parameter and 5 should not. Now, the margin of error depends on 3 factors: your level of confidence. If you want to get more, if you want to be super accurate, you're going to have cast a wider net, essentially. If your confidence increases, the margin of error also increases. Your sample size. The more people you ask, your margin of error decreases because the more likely you are getting towards the actual number. And standard deviation of the population, if it's given, the more spread out the data is, it just means the wider the net you're going to have to cast. So the wider our interval for a given level of confidence will have to be. So let's recall the sampling distribution of p hat. Remember that the shape of p hat is approximately normal, which allows us to use the z-table, as long as n times p times 1 minus p is greater than or equal to 10. The mean of the sampling distribution, p hat, is just p. The standard deviation is for sigma is the square root of p times 1 minus p over n. And of course, every trial needs to be independent and sampling from finite populations. So this is stuff that we did in chapter 8, just extending on it. Okay, so we talked about to make a confidence interval, we need p hat and the error. Well, to calculate the error, we're going to have to take the scary looking z alpha over 2 times the square root of p hat times 1 minus p hat over n, these are both, so this is p hat minus it for a lower bound, p hat plus it. Now don't worry about that too much. We'll talk about how to calculate this thing and then add it and subtract it. So suppose a simple random sample size n is taken. A 1 minus alpha times 100% confidence interval per p is given by the following quantities. The lower bound and upper bound are our p hat plus or minus. This is our margin for error. Now, in order to use this, though, we need n times p hat times 1 minus p hat to be greater than or equal to 10. So all the ones in 9.1 will be this way, but when we head to 9.2, they may not be, and we'll talk about how we deal with that. So the margin of error is that second part that's being added and subtracted. Z alpha over 2 is the critical value. That will come from your Z table, but there's only a few of them that are common, so you may just get used to knowing what they are. And the second one is just the standard deviation. So it'll be your mean plus your Z-score times your standard deviation, and then your mean minus your Z-score times your standard deviation. And the Z-score depends on how confident you need to be. So interpreting a confidence interval, a 1 minus alpha times 100% confidence interval indicates that, okay, let's just say like a 95% confidence interval says 95 samples will contain the value of the parameter. 99% confidence interval means 99 out of 100 contain the value. Now, let's talk generally how we're going to do this using our Z table. So for a confidence interval of 95%, that means, remember the whole area under the normal curve is 1. We want to catch the middle 95%. Now if I catch the middle 95%, that means I am not catching 5%. But that 5% is split on both sides. So that means I have to take that 5% and cut it in half, 2.5% on either side. So these are the decimal representations of those. Now, what does the Z table tell us? It tells us the area to the left. So if I wanted to know what our Z value that gives me the middle 95%, I actually need 97.5% to the left. So I'm looking for 0.975 in my table. Now, 0.975 in the table, you look for the Z value, so that's where you look in the middle and go outward, and it turns out that it's 1.96. That means every time you're having a confidence interval, this is going to be 1.96, and because the normal curve is symmetric, that means this one on the other side is negative 1.96. But because we're adding and subtracting, you really just care about the 1.96. The negative is taken care of by the subtraction. So you're really only concerned with the positive one because it'll be added and subtracted respectively. Now, if you want to keep this handy when you're working on it, the most common critical values come from our most common confidence intervals. So if you have a 90% confidence interval, that number will always be 1.645. 95% will be 1.96. 98% is 2.33. 99% is 2.575. Now, in the next video, we will do some full problems, whole examples, and see how we get to our final conclusions for the confidence intervals.